Plus you get all
Oh, okay.
well, somebody should introduce you. This is
Okay.
Olaolu, Ajala, recent PhD, postdoc.
Yes.
What are you going to do next?
I'm working on a startup right now.
Oh,
Yes.
oh, not this.
No, well, not this, no.
Okay.
Okay.
You going to sell stock? Is this your price to earnings here?
No, that's not mine.
No.
Yeah. Thank you.
Well,
Thank you for
thanks
that.
giving us. This looks
Yeah.
like interesting stuff. Is this with Daniel Lieberzon?
Yes,
Okay.
correct. Thank you for your time, everybody. Today I'm going to be talking about an approach to robust synchronization of electric power generators. And this is some work I did with Professor Alejandro Dominguez Garcia and Professor Daniel Lieberzon. I'm going to start with an introduction, talk about the system description, the system we'll be looking at. I'll talk about a leader control design and analysis. Then I'll move on to a follower control design and analysis, and then I'll present some numerical results. So research into synchronization of dynamical systems dates back to the 17th century, to the study of pendulum clocks. And in the physics literature, for example, the famous Picard-Carroll synchronization scheme has generated a lot of activity. In modern control theoretic literature, some prominent tools are dissipativity theory and observer design. And there's a plethora of work on these topics. In the context of electric power systems, however, the Kuromoto type models of coupled phase oscillators has been adopted to describe the behavior of microgrids. And in the context of this work, we'll be looking at the following problem. We're trying to synchronize electric power generators of this form. We consider the problem of synchronizing two electric power systems. You can think of this as a microgrid with the goal of interconnecting them. The first system we'll be looking at is comprised of one generator and one load connected to a bus with voltage support. And the second system is comprised of a single generator. Synchronization in this context entails matching the frequency and angle at the interconnection points. We're assuming that the voltage at this interconnection point is a known constant to both systems. And so we're just going to be focused on matching the frequency and the angle. And when synchronization is achieved, it is then possible to electrically interconnect these two systems effectively. Okay. And in this context, in the literature, synchronization methods are conventionally categorized as manual, assisted manual, or automatic. In the manual approach, a system operator observes the frequency, the phase, and the voltage, and when he sees there's a match at both interconnection points, he flips a switch. In the assisted manual, it's a little bit automated in the sense that if the frequency, angle, and voltage measurements do not match when the switch is flipped, the system would disengage connection. And the automatic is fully automated, where a computer does all that work. Now, however, the robustness of these methods, especially in the presence of measurement disturbances, has not been rigorously analyzed. And so that's what we're going to try to do in this work, as we propose a robust synchronization method for electric power generators. Our approach is based on casting the synchronization problem as an observer design problem. So the follower system I described earlier is going to observe certain states of the leader system, and then it's going to try to mimic those states and other states that are not observed. Okay, now I'm going to talk about the system that we'll be looking at in more detail. So the leader-follower system. The dynamical model for generator 1 takes the following form, where theta describes the absolute phase angle of generator 1, Omega describes the angular frequency of generator 1. UI is the control input. D10 you can think of as a damping coefficient. And L is the electric load, the electric power that's consumed by the load. This is the active power. So in this model, we're assuming that the voltage is 1 per unit, the known constant. On the other hand, the dynamical model for the generator 2 takes the following form. It's similar to that of generator 1, except the load here is 0. Now, the dynamical model for the bus, on the other hand, takes the following form: theta 3 dot equals omega 3. And this is also similar to that of the generator 1, except we have this additional term, which describes the difference in the derivative of the frequencies of generator 1 and the bus. And the load takes the following form. This is similar to the classical model, except for this additional term that comes about by including the first order term in the reduction process, in the model reduction process. Now, the assumptions we're making in this work are the following. The angular frequency measurement of the leader, omega 3, is not available to the follower. So it's only the phase that's been observed. However, corrupted phase angle measurement of the leader is what is observed. So we have this additional disturbance term here, and this is what the follower observes. The voltage support systems of the interconnection points maintain the voltage magnitude at a known constant value. And when our control strategy is initialized, the system operates in steady state. And the initial steady state value of the angles at the bus and at the first generator is known to the follower. So right here, this is the difference, and this is the steady state value. Also, we assume that variations in the electrical load are constrained in size and speed. It follows that the variations in the phase of the generator and the bus will also be constrained. Okay, so now I'm going to talk about the leader control design and analysis. As I mentioned earlier, the goal here is to synchronize these two systems. However, this system has to supply this load with the following control objective. The leader states that are of interest are described as follows. And the purpose of the control is to drive the angular frequency of the bus to a nominal value. So you can think of it as we want the voltage at this bus to be at 60 hertz. Now, for small variations in the load, this is approximately achieved by driving the angular frequency of the generator to a nominal value. Of course, if you assume that it's one pole pair at the generator. And this control objective suggests the following control input. This is simply an integral control. And so under the action of this integral control, the dynamical model for generation 1 takes the following form. And in this work, we're able to show that if the rate of change of the load is constrained as follows, and the initial value of theta is the following. You can get this by setting the derivatives to 0 and solving for theta. Then there exists the following constants, which depend on k, such that choosing the time-varying equilibrium, we have this upper bound. So what we're able to do here is characterize the behavior of this control system by this upper bound. And we can actually show, what we showed is that, and this is straightforward, that C over lambda here is the L infinity induced gain of the system. And this term is an ultimate bound, which means even if the system is oscillating, it would never be greater than, its magnitude would never be greater than this. So this is a bound that characterizes the performance of the control system. And so for low values of k, when we were able to show that, for small, large values of k, we were able to show that this bound is conservative. And I'll show that in the results as we move along. So let's move over to the followers control design and analysis. The objective here is to synchronize these two systems, and the follower states that are of interest are as follows. Synchronization, as I mentioned, the purpose is to ensure that we choose the control input U2 such that the phase and the frequency at generator 2 match those at the bus. And for small variations of load, as we assumed, this is approximately achieved by driving the frequency of the generator to that of the other generator. I'm going to record the assumptions. We assume that the angular frequency of the leader is not available to the follower. A corrupted measurement is assumed. The voltage support maintains the voltage at the bus at a known constant. And when our control strategy is initialized, the system operates in steady state. And finally, variations in electrical load are constrained in size and speed. So we're going to be using these assumptions now. Now, casting the synchronization task as an observer design problem, we propose the following control input. And I'm going to explain why we chose this particular one in a bit. And under the action of this control, this is the resulting dynamical system for generator 2. Now, if we compare the dynamical models for generation 1 and the resulting dynamical model of generation 2, we can understand what this choice of control input is doing. So this is generator 1. If you observe, this is theta 1, right? However, here, this is the following term. Now, if you assume D is 0, and you assume that theta 3 is the steady state value, what you would get here is theta 1 steady state value. So this is theta 1 minus theta 3 plus theta 3, you get theta 1. So what this control input is doing is it is having this system try to mimic this. And likewise here, L of t has the following value. In steady state, this is 0, and L of t is simply this. And so that choice of control input makes generator 2 mimic generator 1. And so if you recall this objective to drive the frequency and angle of the generator to that of the bus, we consider the synchronization error. That's the difference in the frequency of the bus and the frequency of the generator that we're trying to synchronize. And we're able to show that if the difference in if this is bounded, that is the change in the phase is bounded and the change in the frequency is bounded, that the synchronization error satisfies the following bound. Now, this bound, I'm going to show some results to explain it better, but the key point here is that we're able to show that the synchronization error is a function of the disturbance in the system, depending on what the value of k is. So for large values of k, the effect of disturbance on synchronization error will be large, right? And these are modeling parameters. And so the presence of disturbance d of t causes the phase difference to drift. And so as this error is non-zero, the phase difference is going to drift. So if you have two frequencies and they are not exactly the same, the phases are going to drift. And so what's going to happen now is we're controlling the frequency and then we observe the phases. And as soon as they are multiple of 2 pi, we close the switch and we connect. And that's how this synchronization method works. Okay, some results. We've considered the following test case. The initial condition of the leader is set to an equilibrium state. The initial condition of the follower is set to a 0 state. The simulation starts at time 0, and the electrical load is set to a nominal value of 5 per unit. Now at time t equals 5 seconds, the load is perturbed about the nominal value in the following way. The size is constrained to this value, and the rate of change is constrained to this value, where these are positive constants. And for the leader control analysis, we use the following value for the upper limit on the rate of change of the load, and we use the following value for K, and likewise for the rate of change. We have the following results. First, we compared the deviations of the frequency from the nominal value as a function of the load variations. And what you can see is that for large changes in the load, there's a larger deviation from the nominal frequency, which is expected, right? And you can see a similar thing for the rate of change of the load. We compared the bounds for the control design, the theoretical bounds that we had, we compared it to the results. And this is what we had. You can see this is the upper bound. And you can see that as this increases, as the rate of change of load increases, the bound becomes even more conservative. Okay, and yes, the theoretical bound was investigated and found to be valid and conservative. On the other end, the synchronization performance, we analyzed the synchronization error for different values of K and D. And what you can see here is that as the disturbance increases, the synchronization error increases, like I said, likewise with the K. And so using this result, we can choose suitable values of K that can, that for various values of disturbance, the synchronization error will still remain within the expected performance values. So for that system, we tested this and we compared it to the IEEE standards for synchronization error. And what we discovered is that these two values, the system can synchronize because the synchronization error converges to a value that is within the expected bounds. And so at this point, we're able to close the switch and connect the generators. Likewise here. But in this case, for this large value of disturbance, it never fell within the bounds, and so we couldn't connect both systems. So we compared the theoretical bounds that we came up with the behavior of the system. Now for D equals 0.125 pi, the theoretical bound, the equations I showed earlier, suggested this value. And that is what I show here in black. And as you can see, the result falls within those theoretical bounds. Likewise, for the blue, it falls within the theoretical bounds, and for the green. Lastly, we tested this synchronization method, which was developed using a reduced order model. We tested it on an I-order model of the same system, just to see if it works. And yes, it did. And these were the results we got. For these values of disturbance, you're able to close the switch at these points. To summarize, we considered two power systems that are not electrically connected with the ultimate goal of interconnecting them. The first system, the leader, is comprised of one generator and one load. And the second system, the follower, is comprised of one generator. Our first objective was to ensure that the leader's angular frequency tracks a nominal value. Our second objective was to synchronize the leader and the follower. For the first objective, we proposed a control law for the leader and validated our choice using analytical and numerical results. And finally, for the second objective, we proposed a control input for the follower and validated our choice using analytical and numerical results. Thank you. Any questions?
So you say the control input is U2. So I'm just curious, like in a real generator, what does it mean with that U2?
Yeah, it would mean, so if it's a steam generator, it would be how much do you open the valve? By how much do you open the valve? Right? But really, it's a mechanical input. into the system, but and in a yeah, that's what it is.
You have some limit that it cannot go anywhere.
Correct.
So have you considered that the constraint into your problem? Because maybe it asks for something that is not feasible.
Yes. Yes. We didn't look at that specifically, but it can be incorporated into this. Yes. Thanks for that. Yeah.
What was the time scale on that curve?
It was
That one, yeah.
this one. Oh yeah, seconds.
Seconds?
Yes.
So it takes a long time.
Yes, because the generator that we're trying to synchronize starts at 0 speed.
0.
Yes. So we started it from ground. Yeah, from 0. That's why you see this rising up. So it goes all the way to 0.
Okay.
Yeah.
What are the measurements that you need from the grid the generator is trying to connect? It's just the phase?
Yes, just the phase.
But so it's the phase difference with respect to your node, right? I mean, you need some sort of PMU or...
Yes. It's yes. It's just the absolute phase. So yes, it's a phase. Yeah. Yeah, so we assume that that information is sent by a PMU to the follower. Yeah.
Can I have a follow-up question? So you cast the problem in continuous time, but we need to measure the phase using PMU, which is a discrete time, and it may take some time to deliver that information. So will that delay affect the performance of your system? Or no?
I guess that might be something to worth looking into, but my guess would be that if we can get multiple PMU measurements, we can kind of interpolate and you see and kind of see how far the phase is increasing, and then try to match the phase of the follower to that. Yeah. So if there was going to be a delay, we would extrapolate based on the measurements we currently have. Yeah.
I'm just curious, like, what if you want the measurement you receive at this moment, is actually what happened on the system like 1 second before, because of the communication delay or something? Would it
Yeah.
destabilize the system or something?
Yeah. I'll have to look more into that, but I would imagine that the delays are not up to 1 second. I would imagine they're in the millisecond.
Yeah.
Yes. So if we're talking milliseconds, then if we assume that nothing happens between now and the next millisecond, a major event doesn't occur, then I think it should be fine. Yeah. Okay. Okay, thank you.